My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome you all to our International Physics webinar. Today it's our 134 International Physics webinar. Good evening to all here in Bangladesh, and a very good afternoon to all those who are watching this program live from Italy. So hope you are well and safe from Corona pandemic. So we are trying to adjust with this new normal situation. All we know that we cannot continue our normal academic program inside the campus due to the COVID. So, but we have to start our online program. I think you have already come to know that our Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And we have successfully completed our 133rd international physics webinar. Today is our 134th, and today I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Astroparticle Physics Sector, SISSA, Trieste, Italy. And we have with us here today Dr. Enrico, Barausse, Associate Professor, Gravitational Astrophysicist, Astroparticle Physics Sector, SISSA, Trieste, Italy, and he has already connected with us. So I'd like to welcome our speaker. So, sir, good evening and good afternoon to your part, and thanks for joining with us and accepting our invitation. And we would like to say thanks on the behalf of the Department of Physics for accepting our invitation, sir.
Thanks for having me, first of all.
Yeah.
So I'm glad to give this webinar about what I call here the sound of the universe, detecting gravitational waves in space with LIGO.
So yeah, it's my pleasure also, sir. You can carry on.
Thank you. So I've been told this is a program aimed at undergraduate students. So I will say basic things if you know a little bit about this topic. But if you feel the level is too low or too high, please feel free to interrupt at any time and ask questions, and which I will answer to the best of my abilities. So, what are gravitational waves? Well, to discuss what gravitational waves are, let me remind you what is a wave. And if you study physics, well, this is probably familiar to you, but this is also a concept that we encounter in everyday life. A characteristic of waves, be those waves in a medium like water or in space-time like gravitational waves, is that they carry energy and linear momentum. And they travel with a certain speed, a finite speed. Think about sound, for instance. The speed of sound is finite. And in fact, this is a key property of waves, which is also shared by gravitational waves. For a long time, even though gravitational waves were mathematically well-defined and computed within the theory of general relativity, it wasn't clear that gravitational waves carried energy and linear momentum, and we had to wait until the 60s and for a well-defined formulation of what it means for gravitational waves to carry energy and linear momentum. So this is in a sense different from the situation that we have in electromagnetism. We know that light is a wave; it carries energy and linear momentum. It can carry angular momentum. So this is also true for gravitational waves. I just want to convey here the fact that the definition of energy and linear momentum for gravitational waves is much more involved than for other sorts of waves. But nevertheless, gravitational waves do carry energy and momentum, and therefore we have a way to try to detect them. So in fact, gravitational waves are a key prediction of general relativity. So I'm not going to give you a crash course on general relativity. That would be impossible in just 1 hour. Let me say that the key, I mean, again, I don't know what the background of all the students attending this webinar is, but I assume you've seen waves in media before. So general relativity predicts that gravity does not exist. Gravity is just an apparent force. However, it also predicts that space-time itself behaves as a medium. And this medium is curved by the presence of masses. And this is what I try to schematically show in this picture. And what are then gravitational waves? Just like in water, you can have sound waves. You can have waves of this space-time medium, which sometimes we say they are ripples in space-time, and in fact they really are perturbations in the structure, in the very fabric of space-time. They were first predicted by Einstein in 1916. He has two papers on the topic, one in 1916, one in 1918, and they are produced by masses that travel, well, they're produced by any, if you want, moving masses, but they're particularly abundantly produced by masses that are very large, such as those that we encounter in astrophysics, and traveling at speeds close to the speed of light. The thing is, gravitational waves are typically coupled very weakly to detectors. So you know, or you've heard if you're studying physics, that gravity is the weakest among the fundamental interactions, and this has an impact. Even though gravitational waves are produced copiously in astrophysical systems, and as we will see later in systems of two binary black holes, two neutron stars, they couple very weakly to a detector. So, and this is even more true for gravitational waves that we produce here on Earth. When we move around, we do produce gravitational waves. The thing is, they're tiny waves, and they couple very weakly to a detector. So in a sense, you can think of it as the same problem that you encounter when you try to detect dark matter. The coupling of dark matter to the standard model is only guaranteed if you're talking about the gravitation interaction. There is no other guaranteed interaction of dark matter to the standard model. And the problem here with gravitational waves is exactly the same. Gravitational waves only interact by their nature gravitationally with the standard model, hence the difficulty of detecting them. That doesn't mean to say, however, that the energy emitted in gravitational waves, as I will try to explain in the following, is tiny. In fact, gravitational wave emitting sources, such as those that were observed by LIGO and Virgo, and which I will show later, are among the most luminous sources of energy in the universe. It just turns out that this energy is essentially uncoupled to the standard model, all except for the presence of gravity. In fact, you can show, and I give a formula here. I'm not giving many formulas in this webinar, also because I'm not sure about exactly what level each one of you is when it comes to maths and physics. But I wanted to show this formula. This is the luminosity of gravitational waves for a system having a certain mass m. I hope you see my cursor, by the way. A certain mass m, a velocity v, and a characteristic time scale tau. And there's big G and C to the fifth. And if you calculate what this luminosity is for an astrophysical system, so if you consider a system like with mass comparable to the mass of the sun, velocity close to the speed of light, and time scale close to the light crossing time for the sun, you get a huge luminosity. And it just turns out that this luminosity is very weakly coupled to detectors. So I will now explain a little bit how we try to detect gravitational waves. The way we try to detect gravitational waves is by looking at the quadrupolar type deformations induced on material objects. And as I will show in the next, probably next slide, if I remember well, the object I have in mind is really an interferometer, such as LIGO and Virgo. But let me, for the moment, consider the very simple case of a ring of particles. Let's see if I can make this animation work. Suppose we have a ring of particles and a gravitational wave passing by and incident onto the plane of the ring. So the effect of the gravitational wave, which is on purpose extremely magnified here, would be a tiny quadrupolar deformation of this ring of particles. So here again, the effect is magnified by by essentially 15 or 18 orders of magnitude. So if you had or more, in fact, if this LIGO particle was of kilometer scale, the deformation induced by a typical gravitational wave would be a part in 10 to the 18. So and that's, if you think about it, comparable or smaller than the size of a proton. So it's a really tiny effect. So it's really challenging to observe, even if in principle we know that this deformation would be there again for any gravitational wave. In practice, other sources of noise will overshadow this tiny deformation. So how do we detect such a small change of size in a material object? Well, the idea that you also get from everyday life is that of using lasers as rulers. By the way, I can't hear any background noise. Hopefully, you guys are still connected, since there was a problem with the network earlier on. So feel free to interrupt if there is any question. So the idea here is to use lasers as rulers, and this is an idea that again you might be used to in everyday life. For instance, you can find on the internet, or if you're a real estate agent, you'll be used to using lasers to measure distances. There are these nice little devices that allow you to measure the distance between two walls by sending a laser beam and measuring the time it takes for the laser beam to be reflected back to the device. And here, assuming knowledge of the speed of light, the machine can help you measure the distance between the wall and the device itself. So the idea with gravitational waves is really quite similar, although it uses a slightly different concept, that of wave interference. In this case, laser interference. And so interference is, of course, something we're used to from everyday life. So it can be constructive or destructive. And it takes place between two waves of two waves that linearly superimpose. And these waves could be sound waves, could be gravity waves in water, could be light itself, laser in this case. So if you have two lasers and superimpose the electric field and magnetic fields of the waves of the two lasers, interference can be constructive or destructive when it comes to the energy. And the idea here is to use, indeed, interferometry between lasers to measure not the distance between two objects, two mirrors, but really the difference between two distances. So here, this is what we call in technical jargon a Fabry-Perot interferometer, and this is what LIGO, the American, the US gravitational wave detector is like. So you have essentially mirrors at the two ends of the detector, and you have here a semi-transparent mirror, or as we call it sometimes, a beam splitter. So and you have lasers going back and forth between the mirror, each one of the two mirrors, and the beam splitter. And because the beam splitter is semi-transparent, some of the photons that constitute the laser will occasionally go through, and sorry, the other way around. Here you have the laser source, and the laser is reflected upon the mirror, goes back, it's splitted, so it goes to the other mirror, and occasionally it will also go through and reach a collection point. So what you're trying to do is essentially to do interferometry between the two arms, between the two lasers in the two arms of the detector, and this is what we call laser interferometry. So you're trying to measure the difference in the distance between the difference in length between the two arms of the detector due to a passing gravitational wave, in the same way in which in the previous slide I was showing you the formations of this ring of particles. And by using laser interferometry, you're able to measure this to very good accuracy. And again, for LIGO, you're able to measure relative changes in distance between the two arms to an accuracy better than the size of a proton. So it's quite a technological feat. So I've been talking about LIGO, and I'm sorry if you've never heard about this. LIGO is a US gravitational wave detector. By the way, I don't see any faces or anything. So am I still online? Am I still audible? Hello?
Yes, sir. Yes, sir.
Okay. Okay. Just to check, I'm not speaking to myself. Okay. Thank you. So LIGO is constituted of two detection sites in the US. So this gravitational interferometers I showed in the cartoon picture of in the previous slide are actually implemented in practice in various countries on Earth, including one that's close to Bangladesh, India, as I will say in the next slide. But the first two experiments were respectively in the US, LIGO, and in Italy, Virgo. So the first picture is of the two sites of the LIGO detector in the US, in Hanford, in Washington State, in Livingston, in Louisiana. So each one of these is a Fabry-Perot interferometer. And in fact, I think one of the two actually is a double interferometer. I can't remember which one. One of them has a double interferometer. Anyway, so they're essentially what I showed you in the previous slide. And this is the LIGO site in Cascina, Italy, which is also taking data as of now. They're in the observational run number 3. So there are more actually detectors or either planned or under construction online, and I will try to explain why we care about having several detectors. So besides the two LIGOs in the US and Virgo in Italy, there is a smaller detector in Germany, Geo 600, which is actually used to test the LIGO technology. There is a detector which is almost ready to take data, sorry, in Japan, Kagra. Oops. And most importantly, I guess, because of geographical proximity to where you guys are, there are plans to actually dismantle one of the LIGO detectors and reassemble it in India. As far as I know, the site hasn't been decided yet. A number of considerations go into choosing the site of these gravitational wave detectors, in particular seismic stability, proximity to transportation, to airports, etc. But it needs to be in the as close as possible to the southern hemisphere to enhance the sensitivity of these detectors when it comes to localizing sources in the sky. So, of course, if all detectors were in the same, were in the US, if all detectors were in the USA, the network, it would be very difficult to do triangulation and localize sources in the sky, and which is why we try to scatter these detectors across different continents and hopefully also in the southern hemisphere. India is not in the southern hemisphere, but that's as good as we could find. Okay, so why do we need more detectors? And I essentially said this already. When you detect a gravitational wave, you typically, if you just have one single detector, you typically have very poor angular sensitivity when it comes to where the source is in the sky. So this is actually, as you can see, a picture of the starry sky at night with the Milky Way. And superimposed are color plots that show you the uncertainty, if you want, the localization areas where respectively two of the events, gravitational wave events that were detected by LIGO, and of which I will talk in the next few slides, were localized. And as you can see, so the first one, just for the record, it was September 14, 2015, or as we lovingly call it, GW 150914. And as you can see, even though it was, as I will say later, a very strong event, it's hard to pinpoint where it comes in the sky. There are, I don't know if there are millions or billions of galaxies in that area. So it's extremely difficult to try to look for what we call an electromagnetic counterpart, a source of light in optical or X-rays or UV inside that region, because there are so many galaxies that are present in this region. The second event, which was the Boxing Day event, as we call it sometimes, December 26, 2015, is an even larger banana shape on the sky. So, and this is because at that time, only the two LIGO detectors were online. Virgo was not online yet. And just to give you a sense of how much a difference a third detector is, let me show you another famous example, which I will discuss a little bit later. This is GW170817. It's the first neutron star binary ever observed by the humankind. Binary neutron star merger ever observed by the humankind. And this is again the sky. And the light blue area is where you would localize, the LIGO alone would be the green area. So if we only had the two LIGOs, we could localize the source in the green area. And with the addition of a third detector, Virgo, we're able to pinpoint the position much more closely, which is what allowed gamma ray observatories and the general X-ray, UV radio observatories to find what we call an electromagnetic counterpart to this object, which was observed in a range of wavelengths and in the electromagnetic spectrum, and most notably in gamma rays. This is what we call sometimes a gamma ray burst. So this is, I want to say something more about the physics of binary black holes, and there is no better place to start than the first event ever observed by LIGO and by humans. And this was, again, GW150914 in September 2015. And as I said before, this is a huge, it's a very loud event. And this can be seen in the following plot. So this is a plot from the first LIGO-Virgo collaboration paper, even though it was only detected by the two LIGO detectors, as Virgo was undergoing development at that time. And here you see this sort of wavy feature in red and here in blue in the two detectors. And you can see that there's there appears to be what we call sometimes noise. And this noise is due to a number of reasons. It's partly due to thermal noise of the mirrors, because mirrors have a finite temperature. It's due to the lasers, so lasers exert radiation pressure on the mirrors, so they shake the mirrors. Lasers are quantum objects at their basic level, so they have what we call laser shot noise. And last but not least, this noise is also caused by seismic perturbations. So not only earthquakes, but really anthropic activity, trucks passing by, the waves of the ocean. Just to give you a story that I got told once, and which I found very interesting. Even though the Cascina Virgo site in Italy is like 30 kilometers from the sea, they can still hear, quote unquote, in the detector the effect of the sea waves, and that's for us a sort of noise that we want to subtract. So partly it is subtracted here. They do what they call a bandpass filter to produce this nice figure, but it's still visible in the data. And nevertheless, you see that in this region around 0.4 seconds, you have a very large amplitude perturbation, which looks very much what you would expect from the merger of two black holes in general relativity. So in fact, here in the second plot, the red curve is the prediction of general relativity for the gravitational wave signal. And in fact, it matches very well what is in the data. And you can actually see the gravitational wave signal by eye by looking at the data. So this is so far the only event in which we could really look at the noise and see a wave on top of the noise. So this was the first event, but also one of the loudest so far. And in fact, you can see it really in what we call a spectrogram, a frequency time, a power plot. So here, what is plotted is the power in different bins in frequency and time. And we can see this very large excess power in around the peak of this signal. And you can see this parabolic curve, which is what we call sometimes the chirp, because the frequency of these waves increases with time, just like the chirp of a bird. So if you were to convert this gravitational wave into a sound, it would look like a chirping bird to some extent, with a little imagination. So this was the first event, gravitational wave event, ever seen by mankind. It vindicates Einstein's calculations back in the 1910s, and it really is the confirmation that gravitational waves exist and that they do carry energy and linear momentum. Even though for as I was saying, for decades, physicists were dubious about whether these waves carried energy and momentum, and they certainly do, because they deposit this energy momentum on a material object, the LIGO detector in this case. So I've been talking about what a black hole is. When I was an undergraduate, I hadn't, undergraduates don't necessarily know what a black hole is, so I thought I would give just a motivational couple slides about black holes and talk a little bit then about how they're formed. But I want to discuss what a black hole really is according to the theory of general relativity, even though at a very cursory level. So black holes, in fact, the concept of a black hole can be, I mean, it was suggested even before the theory of general relativity. It was suggested in the 18th century based on Newtonian mechanics and under the assumption that light was felt the presence of gravity, which in Newtonian mechanics isn't true. But if you believe that light is bent by Newtonian mechanics, you can still conceive or imagine the presence of an object which is so compact that light cannot escape from it. So again, this is something that becomes rigorous with the theory of general relativity. And in fact, a key prediction of the theory of general relativity is that because there is no free scale in general relativity is scale-free unless you include the cosmological constant, any body of any given mass can become a black hole if it is compact enough. So if you shrink a teaspoon, or if you shrink whatever material object to sufficiently small size, then its gravitational force will become so important that light cannot escape from the interior of the body. And this is really what we call a black hole. We define the black hole as its event horizon, so the region of space-time from which light can never escape. And one important thing which is needed to understand a little bit the basics of gravitational wave physics is that the event horizon, as predicted by general relativity, is proportional to the mass of the object. So if I have in fact, maybe I have it in the next slide, let me see. Yeah, I have some orders of magnitude in the next slide. So the size of a black hole is proportional to its mass. Otherwise, it wouldn't be a black hole. It wouldn't be compact enough to capture light in its interior. So in the case of the two black holes that were observed by LIGO on September 14th, 2015, the mass that we believe they have is about 29 and 36 times the mass of the Sun. So mass of the sun, just as an order of magnitude, is 2 times 10 to the 30 kilograms. So I Googled it, and it's about 300,000 times larger than the mass of the Earth. And the radius of the sun, for comparison, is 10 to the 6 kilometers, roughly, within an order of magnitude. The radius of these black holes, which were, again, about 30 times larger in mass or heavier than the sun, was only of 87 and 108 kilometers, respectively. So if you were to concentrate the mass of 30 suns into roughly 100 kilometers, you would get a huge density. And so if you were to take this is something curiosity. I mean, if you convert to metric, if you could actually with a teaspoon take away a little bit of these black holes, you would have an incredible weight. So they're very so in a sense, gravitational waves, black holes are very compact and dense objects. So how do you did you actually form these black holes? So here I'm not gonna again give you a crash course in stellar evolution. I didn't know this stuff when I was an undergrad, and it's not necessarily interesting for all of you, but at least I hope I will stimulate the curiosity of at least some among you. The way we think we form astrophysical black holes is via supernova explosion. So we know supernova explode in the sky. We do observe them every year, very frequently, sometimes even close to us. One of the first historically recorded supernova was by the Chinese, I think in right after year 1000 in the Christian calendar. And we have a pretty good understanding by now how supernovae, especially what we call type 2 supernovae, explode, what we would call ordinary supernovae. So without entering into the details of stellar evolution, stars, or the sun as well, they get their energy, the energy they radiate, via nuclear fusion. So if you start with a hydrogen star, by nuclear fusion, you'll then produce helium through a sequence of reactions that produce energy. And you produce a helium core. Then once you don't have once you have enough helium and sufficiently less hydrogen that it becomes energetically or statistically favorable to produce carbon, you produce carbon, and so on and so forth with the heavier elements, what in astrophysical jargon we call metals. In astrophysics, we call metals anything that's heavier than helium. So from carbon, you create neon and then oxygen, silicon. At some point, you start creating iron. So iron is the element with which is the most stable among the elements. So it's the one with the minimum binding energy for the nucleons. So if you try to then produce elements which are heavier than iron, I'm not sure what there is after iron, I can't remember, but if you try to produce by nuclear reaction elements which are heavier than iron, you wouldn't be able to do that inside the star. You would need to inject energy in the system. And this causes a catastrophic instability that gives rise to supernova explosions. So this is how run-of-the-mill black holes with masses about 10, 15 solar masses are produced. There is also another way to produce, and the endpoint of this supernova explosion can be, according to the mass of the star, a black hole. So the core, the iron core, would collapse. The outer layers of the star would be ejected away. The central core would undergo gravitational collapse because it wouldn't be supported by radiation anymore, and it can give rise to either a neutron star or a black hole, as I will discuss in the next slide. There is also another class of supernovae which are much less understood theoretically and also observationally. because they are believed to be important only for very large, low metallicity stars. So if you start with stars that are very massive, at least 100, 200 times the mass of the sun, and these if these stars are mainly constituted by hydrogen, so they have very little metals. Another instability can occur, so you can create heavier elements. At some point, however, the temperature of the star will be so large because of the high mass of the star that photons would start colliding with one another and producing electron-positron pairs. So this would decrease the radiation pressure and cause also a catastrophic instability. And this is what we call a pair instability supernova. Pair instability because it's really triggered by the production of electron-positron pairs inside these very massive stars. And we believe that in LIGO we've seen the end products of both supernova types of explosion, because even here the endpoint of the instability can be a black hole. Well, here this is a bit more quantitative. I'm sorry for there are many labels in this plot, but this is just to give you an idea of what the endpoint of a supernova explosion is as a function of the initial mass of the star in the x-axis and metallicity in the y-axis. So metallicity here, remember, in astrophysics we call metals anything heavier than helium. So if the initial mass of the star is between 9 and about 25, 30 solar masses, supernova explosions would create a neutron star. And I mentioned before the supernova observed by the Chinese in year 1000, we can still see the pulsar left behind by that supernova explosion. Pulsars are neutron stars, and we do observe them exactly in the sky location where the Chinese astronomers a millennium ago saw the explosion of the supernova. And at higher masses for your star, you can create black holes directly by in the black area here. You can create black holes by fallback, so material from the explosion can fall back onto the core and trigger gravitational collapse. Or in some cases, you may not form anything at all. And this is what we call sometimes the pair instability gap, which is a very exciting field of research nowadays. I'm running a bit behind on time, so I should speed up, I think. I believe I have an hour, right? Or how long should I speak?
I think you can carry, because it will 1 hour.
Okay. I should be able to.
Maybe 40 minutes. So
it's 40 minutes. Okay, so I'll try to speed up a little bit. So I mentioned, that the endpoint of gravitational collapse can be neutron stars, and in fact, I already gave you a spoiler. I mentioned that LIGO has seen a merger of 2 neutron stars, and unfortunately, I don't have a nice picture to show you, such as the one I had before for black holes, mainly because neutron star mergers are typically less loud than black hole mergers. So I can't show you a wavelet with some noise superimposed, because by eye you wouldn't see anything. However, by statistical technique, match filtering, Bayesian statistical analysis, etc., we can extract this signal from what we call the experimental noise. And so what I show you here, just to give you an idea without entering too much in the detail, is the frequency, this excess power plot that I showed you before for black holes. So again, frequency in the y-axis, time in the x-axis. And you can see here in the LIGO-Livingstone plot, this track, this chirp. So this increasing frequency track, which is really the first neutron star binary merger observed by LIGO and Virgo. And you can see hints of it here. You cannot see a thing in Virgo. And the reason is not that Virgo is inherently less sensitive than LIGO. It's because it was in one of the blind spots for Virgo. So the gravitational wave detectors have a certain sky antenna pattern, and this event turned out to be outside the Virgo antenna pattern, which or in one of the blind spots, which actually helped identify the position in the sky. Because Virgo didn't see it, and because the event was strong enough, we knew that it had to be in one of the blind spots of Virgo. And most importantly, there was also a coincident detection by Fermi of a gamma ray burst dubbed 1708-17A, which just 2-second delay in a sky position compatible with the one of the gravitational wave source. And this is something that helped solving the long-standing question of whether really gamma ray bursts, in particular short gamma ray bursts, are connected with neutron star mergers. This was something that was hypothesized before, and for the first time, we managed to ascertain that there is indeed a connection, that short gamma ray bursts are neutron star mergers. There are many more detections that I can talk about. You can find plenty of material online, webinars and talks. I can point you to papers, anything. There were about 10, 11 detections in 2018, and this is what we call observation RAM number 1 and 2. Only one neutron star merger, all the other are black holes. And it's quite interesting to think about the distribution in masses. So black holes typically have masses of about 30 or larger solar masses. Neutron stars have masses about 1.5, at most 2 solar masses, or they're down here. And here you also see in purple the black hole binaries that were proposed as possible candidates based on X-ray observations. There are a number of X-ray emitting systems for which which people believed to be, and probably rightly believed to be binary black holes. However, they typically have slightly lower masses than the masses observed by LIGO and Virgo. And this is sort of strange and something that people are still trying to understand. Why is the population of black holes that we observe with LIGO and Virgo apparently more massive or different than the population of black holes that we see in X-rays? Is it simple astrophysics? Is there a more fundamental reason? We don't know. Neutron stars instead are the neutron stars that were seen to merge in LIGO Virgo are very similar to the neutron stars that were observed, for instance, in isolation or in binary pulsar systems. So they're very typical from that point of view. There were even more detections in 2020, so things are growing exponentially. So when LIGO is fully operational in design sensitivity, it will detect a merger a week. So this is an incomplete list of what they saw in the first part of the observation run number 3. So I can't enter into the details of this population. Let me just show you, well, and let's skip this one. This is another table of the same events. Well, let me show you just graphically what happens. So this is the same plot as before, but now to make it less cluttered, they've only put the systems observed by LIGO and Virgo. There is possibly a second neutron star merger that they put here. It's not very robust. It's not clear if this system is a neutron star merger. It could be a neutron star merger. It could be, yeah, it's the false alarm rate. Statistically, it's not clear that this is a neutron star merger, also because they didn't see any gamma rays associated with it. But as you can see, the same for black holes, which are here in blue, the same trend survives. So we typically observe very large masses with LIGO and Virgo. And we even observed black holes, which are 100 solar masses. And this is remarkable because according to our current understanding of astrophysics, those black holes shouldn't exist. So they fall into that pair instability gap where pair instability supernovae shouldn't leave black hole remnants behind. And this is a huge open question, how these very massive black holes observed by LIGO and Virgo form. Is our understanding of stellar evolution completely wrong? Or at least our understanding of the pair instability mechanism wrong? We don't know. That's a something which is very recent and one topic that people are talking about, are thinking about now. In the last 10 minutes, perhaps, I want to go to the real topic. So I titled this talk, observing the, what was it, hearing the sound of the universe with Lisa, because this is my favorite topic. But then in the course of why I prepared this lecture, I thought it was more interesting to talk about LIGO. But let me say, let me get to the Lisa part. And then if I don't get to the end, you're welcome to ask questions later. The black holes that we observe with LIGO are not the biggest black holes that we observe in the universe. In fact, there is one, I call it here a monster black hole, because it's about 4 million times larger than the sun. Sorry, there is a typo here, 4.5 million solar masses in the center of our galaxy. So this is 4.5 million times the mass of the sun in the center of our galaxy. So a Nobel Prize was awarded, this year for the discovery of these black holes, which dates back 20 years now. Essentially, what they do is to really use Kepler's law. So they use Newtonian mechanics. They observe S stars, what they call S stars. They're essentially stars like the sun, main sequence stars. And they seem to orbit a point-like dark mass at the center of our galaxy, and there is nothing there. There is no electromagnetic emission from that point. But using Kepler's law, you can infer the mass, and it's a huge mass, 4.5 million solar masses. And also, this object needs to be very compact, because otherwise, stars would actually bump into its surface. So we can exclude both because of the very high mass and also because of these S stars, that this can be anything but a black hole. There are some exotic alternatives, but they require, exotic physics that not many people believe in. So for the Nobel Prize Committee, this was a black hole. The Nobel Prize was awarded for the discovery of a black hole. So the question is, can these black holes merge as well? Because and in fact, one of the things that one of the paradigms of nowadays astrophysics or galactic astrophysics is that black holes, such as the one in the center of our own galaxy, inhabit essentially all galaxies in the local universe at low redshifts, especially in large ellipticals, but also in dwarf galaxies. And one of the key discoveries of astrophysics in the last 20 years is the realization that there is a correlation between the mass of these black holes and the size of the galaxy. This is the famous M sigma relation. So I don't want to enter into the details here, but let's say virtually every galaxy has a supermassive black hole, supermassive meaning at least 1 million solar masses, but up until 1 billion or 10 billion solar masses at the center. And also, we all believe that the universe is what described by the concordance lambda CDM model, and for which other Nobel Prizes were awarded, of course. And in the lambda CDM model, galaxies form hierarchically. So you start with small dark matter halos at high redshifts, and these dark matter halos, or galaxies, if you will, they will merge slowly as cosmic time increases, as you get to the very big elliptical galaxies that we see today at time 0. And of course, if galaxies merge, you would expect that also the contained black holes would merge. And in fact, this is a bit the idea. Galaxies merge, and we see them merging. We see galaxies that are in the process of merging when we look at the sky with the optical telescopes and in other wavelengths as well. And therefore, we expect supermassive black holes will also merge. And in fact, there's a lot of interesting physics, astrophysics, that you can explore, because another paradigm of galaxy formation today is that supermassive black holes are not just passive actors in the history of the universe. they don't just sit at the center of galaxies and do nothing. They actually eat gas from the surroundings, and they shine as quasars. This is what we believe quasars are since the 60s. And also, we believe that they also backreact or inject energy in the surrounding medium. So this is a picture of M87, yeah. So and here you see that this is the same galaxy that was observed by the Event Horizon Telescope, just in case you've heard about it. So the same black hole that's been observed by the Event Horizon Telescope, and we see the black hole injecting, if you want, a jet into the surrounding medium, heating it up. So this is what we call AGN feedback, and it's crucial for our understanding of galaxy formation. It's crucial to explain the properties of large elliptical galaxies that we see today. So there is a two-way street between black holes and galaxies, and one that we hope to be able to observe using or to probe using gravitational waves. What's the problem in the last 5 minutes? Gravitational waves from massive black holes have much lower frequency than gravitational waves from black holes of masses comparable to the sun, like those that we observe in LIGO. And this is really due by the scale invariance of general relativity. So in general relativity, there is no fixed scale. So so for a black hole binary system, the only physical scale is the mass. Essentially, if you're close to merger, the only scale relevant for the problem is the mass, or if you want, Schwarzschild radius of the two black holes. And simply by dimensional analysis, you can conclude that the frequency of the gravitational waves from a system of total mass m will be inversely proportional to the mass of the system. So the bigger the black holes you want to observe, the lower in frequency you have to go. And this is a problem because I mentioned before seismic noise in LIGO and Virgo. Seismic noise is actually the dominant source of noise on Earth at frequencies about 10 hertz or lower. So this is what we call the sensitivity curve of gravitational wave detectors. So the lower these curves are, the better the sensitivity of gravitational wave detectors. And these are here on the right are ground-based detectors, and you all see their sensitivity gets worse at frequencies of 110 hertz due to the seismic noise. So if you want to observe 10 to the 6 solar mass black holes, like those in the Milky Way, you need to go to millihertz frequency. If you want to observe a billion solar masses black holes, you need to go to nanohertz frequency. So you need, and you can't do this on Earth. There is no way you can do this on Earth. Yeah, sorry, this slide was making the point, exactly the point I was making before. This is the sensitivity curve for, I think, for Virgo. Yeah, for Virgo, in fact. And you see here the effect of geophysics, what we call the seismic noise that degrades the sensitivity of the detector at low frequency. Okay, so if you have something that you can't do on Earth, you can go in space if you have enough money. And this is what we want to do with LISA, the Laser Interferometer Space Antenna. So LISA is a joint mission by ESA, the European Space Agency, and NASA, the American agency. And it's essentially a Michelson-Morley interferometer in the sky. So we want to fly 3 spacecraft, trailing the Earth around the Sun, about 20 degrees behind the Earth, exchanging laser beams over 2.5 gigameters distances, 2.5 million kilometers distances. And if you think about it, from the engineering point of view, it's a huge feat just to fly lasers for millions of kilometers in space and far from the Earth. So you can calculate how long it would take to send a radio signal from the Earth to the spacecraft, to maneuver the spacecraft. It's not trivial at all from a technological point of view, but it's actually funded. It's fully funded. We are in the process. Soon we'll start with industrial production. There were prototype missions flown in 2015, the so-called SISSA Pathfinder. I believe I have a slide later on that. So we're quite confident that the launch will happen if there is no other pandemic from now till 2034 will happen around this date. And with that, we'll be able to observe supermassive black holes of masses 10 to the 6, 10 to the 7 solar masses up to huge redshifts. Redshift 20. If you've ever took a course in cosmology, you know that we're not even sure galaxies exist at redshift 20. So yeah, so I'm almost finished. Last 2-3 minutes. As I mentioned, this is a hugely costly and challenging technological feat, which is why ESA actually tested a scaled-down version of LISA, just one arm of 40 centimeters, in 2015-16, the so-called LISA Pathfinder mission, and it worked perfectly. So I'm not going to the details of what this plot is, but this was to test our ability to put test masses in free fall and reduce to the minimum the noise due to gas still present in the vacuum chamber, to solar wind, to electrostatic charges. There are a number of sources of noise that you have to control to put masses in free fall in space, which is what you need to measure gravitational waves. And then to go from 40 centimeters to 2.5 million kilometers is not trivial from an engineering point of view, because the laser will weaken because it has a certain convergence angle or focusing angle, but it's less delicate than being able to put test masses in free fall. Let's see what I have next. Maybe let me skip this slide. This is just to say that we expect, it's very hard to predict the future, and we learned it in LIGO. In LIGO, we observed black holes that were way more massive than we expected based on X-ray observations. For LISA, you can try your best to simulate the universe and calculate how many supermassive black holes should be detected by LISA, and this is what I work on, and I'm quite confident the number will be larger than zero. But the range that you get can go from a handful to hundreds. So, and this is something that we learn once we have LISA. We'll be able to, if you want to, solve the inverse problem of trying to use the number of detections that we get from LISA, and also the parameters, the masses of the black holes that we measure, to infer information about the astrophysics, about feedback, for instance, about accretion, about the connection between massive black holes and quasars. Okay, let me see what I have in the next slide. Yeah, maybe I have a few more slides about things, all the wonderful things that you can do with LISA, but I've been talking for an hour according to my watch. So maybe I'll skip these slides, which were, if you want, just an appendix, and just say in the last minute a couple words about one more gravitational wave experiment, gravitational wave detector, which has the advantage of being active now, and this is what we call pulsar timing arrays. So EPTA, nanograv, PPTA are all experiments that try to use pulsars to detect gravitational waves. The idea is that pulsars are rotating magnetized neutron stars. I don't have an animation here. They essentially look like, they're neutron stars which are magnetized, and the magnetic axis is misaligned with the rotation axis. So whenever the axis of the magnetic field points at you, the pulsar will send you a radio pulse. And the pulsars were discovered many decades ago, and some of them, in particular millisecond pulsars, are very precise clocks. So the pulse that you get, once you average over what we call the weather of the pulsar. That's maybe a detail. If you calculate the time of arrival of the different pulses, they are very regular. If you consider what we call a millisecond pulsar, they're more precise than atomic clocks. So it's like having a system of atomic clocks in the sky. And if a gravitational wave passes by between the pulsar and the Earth, it will change the distance of the pulsar from the pulsar to you. I remember the analogy of the laser ruler that I gave in the beginning. So here it's really a laser ruler. So the pulsar will get closer or more distant from you, and therefore the time of arrival of the pulse, of the radio pulse, will change. And this is how we try to detect gravitational waves in the nanohertz band. And again, this is a frequency range which is sensitive to black holes of about billion solar masses, 10 to the 9 solar masses. And why is this important? Because, well, these experiments are taking data as of now. There are experiments in the US, in Europe, in Australia, and we're in the ballpark of the predictions of all astrophysical models. So these are predictions of astrophysical models, the dots here, various astrophysical models. And the region that was excluded by these experiments up until last year was this shaded area here. So some models were already being excluded, some astrophysical models. And even more importantly, and then I will close, there was a paper about 5 months ago where the nanograv, the American experiment, finds tentative evidence for a possible gravitational wave signal in their data. And in fact, they revised their previous upper bound, so they reanalyzed their data with different assumptions for the priors, and they now believe that there might be something in this band. This A here is the amplitude, the log amplitude of the gravitational wave signal, in a sense. And this would be in perfect agreement with what we expect from astrophysical models. It's still, the judge is still out because, and I can explain if you want why, even the nanograv experimental team, they're not, they don't claim yet a gravitational wave detection, but there is definitely something here that needs to be understood. So I'll stop here. Sorry for going over time. I don't have a conclusion slide, so I think we're just a motivational one, perhaps, since I guess I'm talking to young people. Gravitational waves are a relatively new field. As far as data are concerned, so we've only had data for the past 5 years, but they have the potential, and to some extent are already opening a new window on the universe. Just like for millennia, the humankind looked at the sky in optical electromagnetic waves, and when we started looking at the sky in other bands, the sky looks very different in gamma rays or in X-rays than in the optical. So I think the same will be true in gravitational waves. So far, we've been looking at gravitational waves at frequencies of larger than 1 Hertz, 10 Hertz, 100 Hertz. With LISA and in general with other space-based detectors like PTAs, will be able to go to much lower frequencies, and I'm sure there will be plenty of surprises. Because there are certainly more things in the universe than we can think of in our natural philosophy. To quote Shakespeare. But yeah, that's all I wanted to say. And if there are any questions, I'm happy to answer. I hope the level was all right. If you want more details about more technical details, I'm happy to answer any questions.
Yeah, thank you, sir, for your wonderful presentation. And I think the students have learned a lot of things about the gravitational wave and astrophysical, the topic you have explained. So I think they have learned the new technology also, like LISA. So we have got some question, and we have a guest from India with us. So if you allow, we can start our discussion session.
Absolutely.
So Raz, have you connected with us?
Yeah. Yes, sir. Yes.
So if you have any question, you can ask our professor.
At first, hello, Professor Enrico. Hardly welcome. I am an Indian PhD student, recently joined PhD student, and very much motivated in astrophysics and cosmology. Now my coursework is all going on, so I am not decided yet of my subject, but I am very much motivated in astrophysics and cosmology. So from your top, I have two questions. So if you allow, so I'll say one by one.
Of course, yeah. Please go ahead.
So my first question, you have said at first, we all know the theory of gravitational waves when the space-time ripple generating, and so my questions, in that space-time ripple which generated as a propagation of gravitational wave, is there any effect on it of universe expansion? I mean, or very specifically, there is any effect or any interaction with dark energy to this gravitational wave or gravitational radiation? It is my first question.
Okay, so yeah, I can answer this question as you asked the second one. So there is definitely, maybe can you mute yourself because I hear an echo, I hear myself. Yeah.
I have muted.
Okay. No, it's all right now. Yeah, there is definitely an effect of the universe expansion on the gravitational wave signal. However, if you just assume that there is no cosmological constant, as I was saying before, gravitational wave GR is scale invariant. So there is no, if you think about the Einstein equations, there is no dimension full parameter in the Einstein equations, and therefore the universe expansion appears in the waveforms as a renormalization of masses and frequencies. So the masses that we measure with gravitational wave detectors are not really the true physical masses, but they are what we call the redshifted masses. So the masses at the source, the masses of the source times 1 plus z, the redshift. And this is one of the problems of gravitational wave physics, that we have to disentangle the effect of the redshift in order to measure the masses that we're interested in if we want to do astrophysics. So the way we do it is gravitational waves also provide a measurement of the luminosity distance of the source. So we assume a cosmology, we invert the relation between dl and z, and we convert from redshifted masses or detector masses, as we sometimes call them, to bona fide masses, or if you want, to true masses. That said, your other question, you asked about using gravitational waves to test dark energy. There are several ways in which we can do this. One is exactly by what I said. Gravitational waves can measure dl, the luminosity distance. And therefore, if you have an electromagnetic counterpart, such as the one we had for the neutron star merger observed by LIGO and Virgo, we can try to do a distance ladder, just like the one we do with Cepheid or Type 1a supernovae. And this is in fact what was done by LIGO and Virgo, and because their event was local, they could measure the Hubble parameter, the Hubble rate. And so in the future, we'll be able to do much better than that, because we'll have many more events, even especially from the ground. Next generation gravitational wave detectors on the ground, such as the Einstein telescope and similar experiments in the US, will be able to measure essentially all neutron star binaries in the universe up to high redshifts. And neutron star binaries are expected to have a counterpart. So we should be able to do the distance ladder just as we do it now for Type 1a supernovae with neutron star binaries. There's also another side to your question. That I mentioned that this scale invariance of GR is only true when you neglect the gravitational constant. And in fact, you can show that if you put back the gravitational, not gravitational constant, so the lambda, the gravitational constant, if you put back the gravitational constant into the equations for gravitational wave perturbations, it has a small effect on the waveform. So if you put lambda back in the game, GR is no more scale invariant. And especially with LISA, or preferentially with even more sensitive and science fiction detectors, what we call the SIGO, we should be able to see the direct effect of lambda in the gravitational of the gravitational constant in the gravitational waveforms. This is something that has been explored by. I looked at it. Many other people looked at it. So it requires very sensitive detectors. So I'm not sure LISA probably won't be able to do it. But you're young, so and there are plans for detectors such as DSIGO or BBO, which I think stands for Big Bang Observatory, which are even more sensitive than LISA, and those should allow to inform you on lambda. As far as dark energy, dark energy the same. Using distance ladder, you can probably measure the equation of state of dark energy. You can probably measure. You can probably exclude or confirm certain effective field theories of dark energy. This is, in fact, an active field of research. But then it becomes a bit model dependent. So I think the most robust way of testing cosmology with gravitational waves is doing the distance ladder. And there are other ways, but certainly that's the most immediate and clear one.
Thank you, sir. I understand. I understood the matter. So, in the derivations of gravitational wave from the Riemannian tensors, or more technically, if I include the cosmological constant, so this we'll explore that in my question in very much way. Are you getting my point?
Sorry, can you say it again?
I mean to say, if I include the cosmological constant in the mathematical treatment of gravitational wave from the general GR prospectus, so I will explore that.
If you put lambda, the cosmological constant, back in the equations, and you do linear perturbation, so what you will find more technically is that you will have should be a -4 term in the phase. Yeah, so I'm removing my because I hear the echo again. But if you put back the cosmological constant, it will have effect on the phase. It will be a very low PN term. Low PN means it's very important at low frequencies. So and there are papers suggesting, for instance, that if you could observe neutron star binaries with the Einstein telescope, you should be able to measure this term directly in the gravitational wave signal. So if you start from G mu nu plus lambda, R mu nu, the Einstein equations with lambda, and you do the equations, lambda will enter in the equation. So you'll be able to break the degeneracy between mass and spin. I don't know if this answers.
Thank you. I got it. Thank you very much. Can I proceed with my second question?
Yeah, of course.
It is very non-technical question. I want to say that, is there any scope to research on gravitational wave in hardcore theory, or now the research is totally observational?
I do theory. This is it's a matter of taste. By background, I was I did my master thesis in cosmology, then I did my PhD in general relativity. So I do numerical I'm interested both in astrophysical simulations of formation of black hole binaries and numerical relativity simulations in theories that deviate from GR, so effective field theory of dark energy. So I do, in a sense, theoretical research. It depends what you mean by theoretical research. That said, it's true that most of much of the community is now looking at the data, in the sense that we now have data. So when I started as a PhD student, we didn't have any data. So now we have, so soon we'll have a detection a week. So being able to analyze those data and understand Bayesian statistics or other techniques that are used to analyze those data, such as machine learning, convolutional neural network, that is also a hot topic, and one that it depends whether it resonates with what you want to do. So if you want to do theory, I wouldn't discourage you from doing theory.
No, I want to do theory lots. I love theory too much.
Well, I also love theory, and I am a theorist. But sometimes when I look back, I say, I mean, the more you understand the data, the more you find them interesting. That's just a personal feeling. It also depends what you mean by theory. Clearly, yeah, there are people who try to test quantum gravity with gravitational waves. I don't believe that it's possible for the time being, but there are even people who try to do that. So it's a bit of a niche, but there is certainly a community working on quote-unquote theory. Depends what exactly you mean by theory. Certainly,
thank you very much. Thank you very much, and nice to talk you, sir.
Nice
it is a very enjoyable moment to talk with you, and Professor Enrico. Have a good time. Thank you.
Sorry. So we have a question. So how fast does the gravitational wave travel? The question from Faneba. And we have a guest with us, Dr. Qazi Mohammad Rashid Naim, sir. So, sir, have you connected with us? Can you hear us? If you have question, you can ask.
Yes, I can hear you very clearly. Thank you for having.
If you have any question, you can ask.
Okay, not at this moment. I hope
thank you. Yeah, thank you for joining with us. So the question is how fast the gravitational waves travel? Yeah,
the answer is the speed of light to within a part in 10 to the 15, because this was exactly why the coincident detection of the neutron star binary merger in gravitational waves and GRBs was important, because it allowed to put constraints on the difference between the speed of light and the speed of gravitational waves.
Yes, we have another question. So, what is stellar graveyard?
So again, what's the question?
What is stellar graveyard?
I didn't understand.
Okay, so there is another question. So, what is the cosmic catastrophe?
What is the cosmic catastrophe? I don't know.
Yeah.
What's the cosmic catastrophes? I mean, some context might be helpful.
Okay, so this is the last question. So, what is the basic difference between LISA and the LIGO? Yeah,
the main difference is that LIGO, as I was trying to say, cannot see below frequencies of, say, 10 hertz due to the seismic noise, and LISA, by going to space, can go to lower frequencies.
Okay, sir. So thanks, sir. So
thank you. Thanks for having me
here. Yeah, and thanks for wonderful discussion session, sir. So
my pleasure.
Hopefully in near future we will arrange another webinar, and after the COVID we will definitely invite you. And as you have accepted my invitation for face-to-face session in Pabna, so thanks. And we'd like to say
with great pleasure.
Yeah, thanks, sir, for accepting our invitation, and we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation, sir. It was a great webinar, sir, with you, sir. Bye for today. Good night, sir.
Thank you. Thanks for having me. Bye-bye.